Okay. Today we restarting grade 12 probability. This is the entirety of it. So it's not a shortcut from yesterday's lesson, or it's not those of you that want to know, this is one of my students. But for now, let's start. This is probability grade 12. It's the entirety of probability. It includes quite a bit of work. It includes the fundamental counting principle. It includes factorials. It includes arrangements. And includes probability applications. Okay. Um, there's a little bit of NSC and IB work here. It's a full, I would say, 3 exercises, and there's about 18 examples. So let's start. Probability carries around 18 marks in paper one. Most of the time, it's question 10 and 11. Counting questions are some of the shortest questions in the paper. Probably just a few lines, maybe 2 or 3 lines of working out, and you get full marks. It's easy marks, but only if you understand the method, right? From our grade 11 lesson, from our recap lesson, we already learned the probability identities. We learned the Venn diagrams, we learned the tree diagrams, we learned contingency tables. But what we're going to do is we're going to aim for fundamental counting principle, factorial notation. We're going to aim for counting arrangements of different objects in a row. We're going to aim for counting arrangements when some objects are identical. And we're going to count codes and numbers formed with letters and digits without repetition. And then we're going to convert counting results into probabilities. Okay? Please understand, when you're dealing with caps, there's no need to use any permutation formulas. You can use the method that I taught you guys in the other lesson, right? We start off the part one. Part one is the fundamental counting principle. Okay. So for the fundamental counting principle, it's quite simple. We'll take easy stuff again. Let's take one of my students named Sarah. And Sarah decides that she is going out, and she has 3 choices of shirts. Okay. She has shirt blue. She has shirt blue. She has a red shirt. Let's just put this as shirts, right? Okay, so she has a blue shirt, a red shirt, and a green shirt. Now Sarah also decides, hey, I only want to use either jeans or maybe, I don't know, what are the pants? Track pants. Jeans and track pants. Now again, this works very easily when you have 2 choices. When you have 3 choices, maybe even sometimes could be 4. But when it's very small amounts of choices, it's easy to use a tree diagram. The problem happens when it goes to 5, 6, 7, 8, 9, 10, 11, 12. Here, this is only 2 branches and it's fine. Once I start to draw 3 branches, now things become more difficult. And then draw another branch, and you can see it becomes unrealistic to calculate, but also very difficult to draw. So we don't use that. But now, what do we do? For the shirts that my student has, she has 3 choices. And then for the pants, she has 2 choices. And altogether, she has a total of 6 outfits. And that's all there is. This is basically every outcome that she can get is 6. Now, tree diagrams, again, will only work for small problems. But once the numbers start to grow, you have to use the fundamental counting principle. Now, the fundamental counting principle is fine. There's ways to do it, but there's also no need to panic and no need to stress. Take choice 1 times choice 2. times the number of choice 3 times the number of choice 4. And then you just leave it as is, right? So let's take a question. My other student, Chaviso, she decides to go out for lunch with one of her friends. And for lunch, she says she wants to be fancy and have a 3-course meal. So for the starters, they tell her, listen, you have 3 choices. For the main course, they tell her, nope, you can have 5 choices. And for desserts, they tell her that she can have 4 choices. So if we use the fundamental counting principle, I want you to understand that the total meals that you could have, the total decisions that can be made is 60. 60 different outcomes. And that's all there is. So again, if we go with another this thing, let's say we have a student named, a very short student named Aradia. Now, this student is playing a game with a family member, and she decides to roll a dice. Okay. And her cousin decides to flip a coin. And if you want to find out how many possible outcomes there are, we look at the dice, and the total number of outcomes on the one dice is 6 because it goes 1, 2, 3, 4, 5, 6. And for a coin, it's heads and tails. So it's only 2. So the number of outcomes that we can get is 12. So there's only 12 outcomes. Let's go with, okay, let's go with a little bit of a, let's say, not too difficult question, but does take some effort. Let's start here. Okay. So the number plate consists of 3 letters. This is no vowels. There's no vowels allowed, right? So that's A, E, I, O, U. Followed by 3 digits, 0 to 9. This is 10 options. How many number plates are possible? A, if letters and digits may be repeated. So you can use the slot method. 1, 2, 3, 4, 5, and 6. Okay. Now we're not looking for placements. We're looking for how many options can be done. So let's start with one thing first, right? If letters can be repeated, there's 26 letters in the alphabet. So 26 minus the 5 vowels will be 21 letters. So for the first code, we're allowed to put 21 letters. For the second one, we're allowed to put 21. For the third one, we're allowed to put 21. Numbers are 0 to 9, which is 10 numbers, 10 numbers, 10 numbers. And now when we start to multiply, we end up with some 9 million, some change, I think. So this becomes 9,261,000, and we're good. Now, question B states that numbers and letters can't be repeated. So I'm just going to copy this because I'm a bit lazy to redraw it. But numbers and letters can't be repeated. So let's start. For the first option, we can have 21 A, B, C, D, E, F, G minus the vowels. For the second one, because we already used 1, we get 20 and then 19. Right? The reason is, guys, I don't feel like writing A, B, C, D all the way to Z, but please understand we have a total of 21 letters that we can use for the first one. For the second one, because we used 1 letter already, we only have 20. And for the third one, because we used 2 letters, we only have 19. The next part, 10, 10, 10. This would be 10, 9, and 8. And the total of this is 5745, 600. Again, the numbers can't be repeated. So it goes 10, 9, 8, and it stops at that point. Okay, the next part we're going to deal with, part 2 would be all of the factorial. Okay. Now, when it comes to factorials, on your calculator, it looks something like this, if I'm not mistaken. And when a number of different objects are arranged in a row, the first slot has n choices. The next slot will be n minus 1, and then it'll continue. So what that means is, if I gave you something like 10 factorial, this would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? So the one doesn't matter, but generally this would be n, and then this would be n minus 1, n minus 2, n minus 3, n minus 4, all the way until it just ends up as 1. Okay? It's going to end up right there by 1, but there's no need to panic, right? Now, what I need you to understand is there's a special definition, 0 factorial technically equals to 1. So let's go and try that one and see what happens. 0 factorial equals to 1. So now we learned that one. So the mistakes that I see people making are quite simple. Mistake 1 is that sometimes, how do I put this? Sometimes people would see 4 factorial multiplied by 3 factorial and think it's equal to 12 factorial. That's not correct. Okay. Sometimes people would see 6 factorial over 4 factorial and think they can simplify this to 3 over 2 factorial. That's not correct as well. You always expand, okay? Expand, then cancel. Okay? That's how factorials work. So in general, 8 factorial over 6 factorial. I guess this is easy because I have 6 factorial on the bottom. I'm going to open the 8 up. So that's 8 times 7. Look at this, times 6 times 5 times 4 times 3 times 2 times 1. Right? All over 6 factorial. Now guys, pay attention. 6 factorial is the same as saying 6 times 5 times 4 times 3 times 2 times 1. So it means that this part, see this part here? Realistically, what this is we can go 8 times 7 times 6 factorial all over 6 factorial. And we can cancel, and 8 times 7 is 56. That's all there is to this question. If we take the next one, let's do the next one. So this would be 10 factorial over 7 factorial multiplied by 3 factorial. Okay. Now I would simplify. Let's go with it. 10 times 9 times 8 times 7. I'm going to stop at the 7 factorial because I have a 7 factorial on the bottom. Right. Let's do it part by part. So once I cancel and cancel, let's go with 10 times 9 times 8 should be 720. All over 3 factorial is just 3 times 2 times 1. So this is 720 over 6, and that equals to 120. And that's how we deal with factorials. Okay. Now we're going to start to deal with arranging different objects in a row. Okay. Part 3 is that's arranging. That's different objects in a row. Now, if there's a number of objects in a row, and it can be arranged in a number factorial ways, like if I tell you, hey, my student Aya has 6 books, right? She has 6 books and she wants to put it on a bookshelf. How can she arrange it? Of course, it could be 6, 5, 4, 3, 2, 1. Therefore, it is 6 factorial, which is equal to 720 ways. Okay, guys, when we are arranging different objects in a row, the number of objects is quite easy to deal with. We just did that before. We can say n, they use n, so don't be confused. But the first question is restriction type 1, fixed position. So we have 2 parents and 3 children standing in a row for a photograph. In how many ways can they stand if the parents must stand at the 2 ends? So guys, altogether, there are 5 people, but the parents have to stand at the end. So again, this will be, let's say dad, mom. This will be child 1, child 2, and child 3. Okay. Now let's sort out the restricted parts first. So if we put for part 1, we have 2 choices, either the mother or father. For the last end, we only have 1 choice because if the father was in part 1, in the first slot, he can't be in the second slot. So that part is easy because the first part, the first block can either be the father or mother. The last block could either be one of them only, because if the father's in the first one, the mother has to be last. If the mother's in the first one, the father has to be last. But now, next to the first choice, we have 3 children. There's 3 children that can be there, and that's fine. But no matter what happens, one child will be here. So if one child's there, that means in the next block, we only have place for 2 children. And if one child goes there, that means in the last block, we only have place for 1 child. So again, in the first block, all 3 children fight for the space, and 1 child stays there. In the next block, only 2 children can fit there. And in the last block, only 1 child can be there. And when we deal with this should be 12 ways because we multiply all of them. And that should be the end of this question. But again, it's quite simple to deal with if we move forward. I will explain one more time. Again, I will explain one more time. Look at this. You see, guys, in this block, let's say we got, I don't know, Jeff is a father. I don't know. Jeff, never mind. I don't want to use real people's name. Sam is a mother. Children, we call them Aya, Caden, and Sarah. Guys, these are the 3 children. No matter what happens, we don't know which parent is here. This has to be a parent. So either way, it's either Sam or Jeff, the parent. But if one parent stays over here, if just say Sam decides to stay there was 2 choices, but Sam decides to stay there. That means in the last block, there's only 1 parent that can stay here, which is Jeff. So this was 2 choices, and that's 1 choice. Now, for the 3 children, we have Aya, we have Caden, and we have Sarah in the first block. They're all fighting for this first block, but the winner is obviously Aya. So Aya wins, and she gets to stay in that block. But there was 3 choices for this block. Now, if Aya stays in that block, there's only Caden and Sarah for this block. Now, for this block, the 2 of them fight, and there's 2 choices. But obviously, one's going to win, it's Sarah. And the last block, we got Caden, and he's just chilling there. For his block, there's no competition because there's no place. So it's there. So we multiply, and we should be good. Okay, guys, the next question is restriction. It's type 2. It's objects that must be tied together. So you tie them to one block, and you can arrange the blocks as is. Okay. So they say there's 3 different math books and 4 different science books, and they placed on a shelf. And in how many ways can the 7 books be arranged if the math books must be next to each other? So this one is a bit difficult at the start, but let's put this as math books, right? See, that's math, that's science, right? So science, 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 allo, allo, oh, allo. Okay, no, wait, I meant math, but I mean it's the same thing, so it's fine. Uh, guys, this is the math books, and these ones must be tied together. So what I want you to know is these books are tied together. You count it as one giant slot. Now, nothing else really matters. This is slot 1, 2, 3, 4, 5. So there's 5 different options. So this will be 5 factorial, right? Because none of the books can be repeated. So that's 5 factorial. We're going to count the math books or LO books as one giant slot because they have to be tied together. Now that's 5 factorial, and that's for all the books. But we must not forget that the math books itself are a different slot. It's 3 different slots. Book 3, 2, 1. So that's multiplied by 3 factorial. And I don't know what that is, but I think 5 factorial is 120. 3 factorial is 6. So that's 720 different options. And that's all there is for this question. Okay, the next one is restriction type 3. Objects that may not be together, right? We can use the complement. You can count all the arrangements and you subtract those where the objects are together. So if we had 5 objects, I'm just giving an example. 1, 2, 3, 4, 5. 5 objects, and that's the total. We can go with this as 5 factorial, of course, right? So there's the formula. Not together would be the total, which is 5 factorial. And you can use the ones that are supposed to be together. So the ones that are together, you can put the 2 that's there, or you could put 4 that's there. But for now, you guys don't understand because we don't have a question. But let's put a question, and then I think things work out quite easy once you see the question. So okay, cool. So 5 learners stand in a row. 2 of them there and there refuse to stand next to each another. And how many ways can the row be formed? Okay, so we got our person there. We'll put the 2 big-headed people over there. They don't want to stand together. And then we'll put all the nice people there. They're okay. They okay standing together. Now, guys, what we need to do is we need to figure out some stuff, right? We need to figure out how many ways we can arrange this if, by some chance, these 2 don't want to stand together, these 2 grumpy people. Let's give one of them a sugar cane. Right. Now, if 5 of them can't stand together, what we need to know is that we take the total first. And the total will be 5 factorial, which is 120. And the next is we need to start tying people together. We need to tie the total people together. Okay. And it's easy. It's easy if they don't want to stay together because we can go and figure out the total. Let me just move some people around. Where's the sugarcane person? Right, guys, there's a shortcut again, right? I did pause because I wanted to help some of my students, but uh, this might seem like it's difficult, but we take the total, which is 5 people. We got 5 people, and that's going to be the total is 5 factorial, which is 120. And then we're going to minus the part they don't want. So we're going to minus the together part. But how do we get this part? You're going to do exactly what we did in the book question. We're going to group these 2 people together that don't want to be together. Let's group and keep them there. We're going to count this one giant, we're going to count this one giant block as 1. And then 1 slot. This is going to be 2 slots, 3 slots, and 4 slots. So this is going to be 4 factorial. But then do not forget that there's 2 people here. So this has to be 2 factorial. Because if there was 3 books or 3 people, it'll be 3 factorial. And 4 factorial times 2 factorial should be 48. So this is 4 factorial times 2 factorial. And this should be minus 48. And altogether, there's 72 choices. And that's all there is to this question. The next one, we can go with quite a simple one. So in how many ways can the letters of the word maths be arranged if the words must start with M and end with S? Say again, guys. Realistically, M, A, T, H, S. There's no need to panic. That's M and that's S. That could be A, T, H. That could be T, H. That could be H. I'm just giving an example, right? We're not using the letters itself, but that's 1 and 1 definitely. That's 3 choices, 2 choices, 1 choice, right? So this would be 1 times 3 times 2 times 1 times 1. You might see this as factorial, like 1 times 3 factorial times 1. It doesn't really matter for small values. And this is 6 arrangements. The good thing about this question is there's no need for formulas. You use the slot method and we get the marks quite simply. The next one, what happens is sometimes there might really be some questions where we have to use the formula for certain questions, but you guys, we can cheat most of it. When I mean cheat, I don't mean physically cheat. I mean use the slot method, right? So now when there's arrangements with identical objects, you see when you swap identical letters, it does not create a new word. So the number of factorials, you can't just say swapping O with O is going to create a new word, right? So we need to always divide by the factorial of each of the values that's repeated. But all of this nonsense is not going to show you anything. Let's deal with a proper word. Let's deal with a proper question, right? So the number of different arrangements of the number of objects where one object repeats is P. So this is the repeating part. And another repeats is Q, and that's another repeating part, and so on. And then it just continues. All the repeating parts on the bottom, right? So you and I are going to pick, let's pick the word needed. Okay? Let's pick the word N, E, E, D, E, D. Cool. Now, guys, what's going to happen is the formula we can just use is we're going to take the total chances, which is here. If we look at it, it's a 1, 2, 3, 4, 5, 6. So we're going to take 6 letters is the total, divided by how many letters is repeated. That's 1, 2, 3. So that's 3 factorial. multiplied by uh, 2 factorial. Sometimes it's just easier to do it with math than to actually try and explain it. 720 with words divided by 12. That's not a factorial, equals to 60. That's all there is to this question. Let's try another one. Let's go with Cassidy. I put 2 S's there. So the total for here is 1, 2, 3, 4, 5, 6, 7. That's 7 factorial divided by the letters that are repeated, which is S and S, 2 factorial. And that's all. So this is total. And this is repeated. And that's all there is to this factorial. I don't know what this answer is, but we can check now. That's 7 factorial is 5040. And that's over 2, which equals to 2520. But that's all there is to this. The next few questions are quite simple. I think we'll make it quite easily. It's called digits and codes. Okay. When it comes to digits and codes, these are good questions. They always come out, digits and codes. Okay. So digit questions it's just straightforward slot work. Read carefully. You need to figure out 3 things. Firstly, for all questions, is repetition allowed? Yeah. Is repetition allowed? Okay. Are there any restricted slots? Okay. Are there any restricted, I'm putting slow, but slots? Whether it's an even number, greater than, or may start off. And then we'll just fill fill these slots first. It's actually 2 things. Fill this first. That's all. So just figure out if repetition is allowed and if there's any restricted slots. That's the only 2 things we need. First question. First question is quite simple. Okay, the 5-digit numbers are formed from digits 1 to 7 with no digits repeated. Right? There's no digits repeated at all for this question, right? So let's deal with it. How many such numbers are possible? Okay, cool. So 5-digit numbers are formed. So there's a 5-digit number, 1, 2, 3, 4, 5. There's 7 numbers available. Look here, 1, 2, 3, 4, 5, 6, 7. Year would be 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. 4, 5, 6, 7. And it would continue, right? 4, 5, 6, 7. And then this will be 5, 6, 7. Now, guys, I'm not using numbers. These are numbers of choices. So for the first digit, we need to know the 7 values that can be there. For the second one is 6, 5, 4, 3. It doesn't go to 1 because it's only 5-digit numbers. And altogether, you're allowed to have 2,520 because you're going to multiply this. But the next one is the number must be even. Okay. So the number must be even. Now, what does even mean? Even means that this last number, um, let's go here, let's go here. So even means that even though we can go 1, 2, 3, 4, 5, 6, 7, 8, oh no, 7, it means we can only use the even numbers. So this is only three choices, right? Now, if we deal with the next part, we can work with it quite simply. Let's go with how many of them are even. So there's only three choices there. We start off with that. What happens with the rest? What had happened? So for the rest, we only get six choices. So for year, we would only get six. So we'll start off here. This could only ever be a major of six choices, right? So we can go with 1, 2, 3, 4, 5, 6, 7. Now understand that one of this has to be even. One of it has to be used there. So there's only six choices there. We go 1, 2, 3, 4, 5, 6, 7. Understand the 2 is already used. And now we pick something like one of the other numbers. Let's just pick 3. 3 is gone, so this has to be 5. Please understand again, 1, 2, 3, 4, 5, 6, 7. The 2 and 3 is gone, right? Plus the 4 is now gone because we picked it for there, so this has to be 4. But this is going to confuse you guys, so let's go back here. No matter what happens, mm, there is 1, 2, 3. There's 3 even, and there's 4 odd, right? I just want to show you guys something. So altogether, there's 7 numbers. So for year, there's only 2 even numbers left and 4 odd, right? So there's only 6 options, right? For the next one, for the next one, it doesn't matter what you take out, but there's only 5 options because we used 1 year. One number is here, 6 minus 1 is 5. Then 5 minus 1 is 4. Then 4 minus 1 is 3. So we end up with this value, 1080. But one more time, please understand that in the last question, there was 3 even numbers. There's only 3 even numbers out of 4. So this has to be 3 because it has to be even. And then for these ones, no matter what happens, let's just write down 1, 2, 3, 4, 5, 6, 7. We use the number 2. So let's take out the number 2 and put it one side. Gone. So there's 6 options there. For year 3, 4, 5, 6, 7. Let's just say we use the number 1. I'm just giving an example. That's gone. Let's say we're using the number 3, right? For the next option, that's 4, 5, 6, 7. Let's just say we're using the number 4. For the next option is 5, 6, 7. So you can see that there's only 3 options, 4 options, 5 options, and 6 options. Please don't confuse these numbers as the numbers we're using. Think of it as the total choices. 3 choices went here. Therefore, there's 6, 5, 4, 3. And that's all there is to this question. Okay, so we'll do this question one more time, just to make sure that everybody understands. We'll start off by drawing the squares, just come up with a different method. There's many ways to do each question. If one way doesn't work out, I'm sure we can always figure out another method. This number had to be even, okay? So 1, 2, 3, 4, 5, 6, 7. Please understand there was only 3 even numbers, so this has to be 3. Now, guys, we used one number here, and there was a total of 7. So we only have 6 numbers left to use here. And if we use one number here, plus one number there, 7 minus 2 is 5. And if we put one number there, that means we use 3 numbers. So 7 minus 3 is 4. Then we use one number here, and 7 minus 4 That is 3. And then we're done. This is with no repetition. But if they asked us for repetition, it doesn't matter, right? Because this would have been 7. If they wanted repetition, it would have been 7 times 7 times 7 times 7. And the last one would be 3 because they wanted an even number. That's all. If they wanted us to repeat numbers, that's all there is to it. But we should be fine. The next question that we deal with would be the bank pin. Please don't try and figure out people's bank passwords with probability. It's not going to work. Maybe it will, but don't go to jail, guys. But okay. Right. Works example 5.2, the bank pin. A bank pin has 4 digits, each from 0 to 9. The digits may repeat. How many pins are possible? Guys, quite simple. Please pay attention. There's only 4 digits, and you're allowed to repeat anything that you want, right? Now, 0 to 9 is 10 digits, so it's just 10, 10, 10, 10. So this should be 10,000 different codes, okay? And then if you bank with a net bank, it's a 5-digit code, so you guys are in trouble. But it's a better thing. So that would be 10,000 different codes. Quite simple, right? But that's only if, that's question A, if they are the same or if they are allowed to be repeated. If they're not allowed to be repeated, then the first one's 10, 9, 8, 7. And then this cuts it down in half. Not half, but it cuts it down. Quite simple. We shouldn't be struggling with this. I do have practice exercises that I'll give you guys at the end, but we have a few more questions, few practice examples, a little bit of probability counting, and we're good. Okay. So the last part of probability for grade 12 would be to understand counting when you're using the counting principle, but then we have to go to probability. Now, guys, the favorable arrangements would be the ones we want to happen. And then the total arrangements is basically the total. It's in the name. Let's go with the first one. If we had a 4-digit PIN, and if it's we choose a random, what is the probability that all 4 digits are different? Now we just did this, right? So the probability that all 4 digits are different, right, would be equal to the total outcomes, which we know is 10,000, right? Because that's everything that could happen if they're not different, over, if we use different codes, that's 50, 40, and that's just 0, 504. We got the 50, 40 from here, guys. All the different codes, and this was the total. That's all there is. We can pick a few more examples, maybe 3 more, and then we can say this video is over, just to make sure that you guys fully understand. Math starts with a vowel. Okay. The letters of maths are arranged at random. What is the probability that arrangement starts with a vowel? Quite simple. Very, very simple, actually. So the total probability. Let's deal with the total. If we go with the total, Okay, guys. Math says five letters. If it can't be repeated, it's five times four times three times two times one, which is 120. If it has to start with a vowel, that's a little bit different because now it changes because vowels, there's only one vowel, A, so that's one, and then the rest is four, three, two, one. Those will be four times three times two, which is 24. And the probability that it starts with a vowel is equal to 24 over 120. It's 24 divided by 120, and that equals to 0.2. But we knew it was a 1 in 5 chance, right? Because, I mean, there's only one vowel, so it would have worked out. And the rest of it I'll leave because generally we're recording this video really late. So I'll give you guys some questions and put it there, and then yeah. And then we can do a test at a later stage. Okay. We'll end the video on this part. Let me just give you guys a test. One, that's two. That's three. That's four. Okay, maybe two more pages, and then we should end. This is exam questions taken from NSC as well. So, yeah, good luck. Maybe we can do this in another lesson. And yeah, that's the practice examples. Okay, good luck, guys.